Hello everyone, welcome to this video. Today we are going to look at the Friedel alkylation. So what is Friedel alkylation? So as the name shows, alkylation, it is the alkylation of aromatic compounds. Relates to the alkylation of aromatic compounds. Okay, R group. Here for R you can substitute as any alkyl group like CH3 like that. So we use for the alkylation, the reagent we use is alkyl halide. Starting material it will be aromatic group and alkyl halide like CH3Cl, and it will form minus HX and forming a aromatic alkyl substituted aromatic compound. So here the catalyst normally used is Lewis acid catalyst. So normally the catalyst are AlCl3, TiCl4, that are Lewis acid catalyst like this, SPF5, BF3, zinc chloride, FeCl3. Okay. This usually happens through a carbenium ion species formation. Okay. So now let us look on to the mechanism. Okay. The initial step is the coordination of the alkyl halide, Rx I will represent as Rx, plus the Lewis acid. I'll here for example aluminum chloride, or here also for halide I will represent as X, and it will form a coordinated species Rx coordinated to aluminum X3 and forming a complex like this. And here this can act as a electrophilic agent. Or in the case the R group can be stable, can form a stable carbenium ion like a tertiary butyl cation. It may also then act as an electrophile also. And what will happen next? This species, this electrophilic reagent, will react with the, I will represent as R plus AlX4 minus. This, since it is electrophilic reagent, so this reaction will be proceeding, forming a R group here, and here there is also a hydrogen, and here there will be a cation. So this will undergo the resonance like this. So positive comes here, and again resonance like this, positive comes here. So I can represent it as so I will represent it as a resonance form. Okay, this species will be formed, and in order to combine this cationic species, it will be accompanied by the anion. Okay, and now the aromaticity is lost. So in order to regain its aromaticity, it will again undergo loss of a proton, minus H plus. Okay, and forming a aromatic alkyl substituted compound. Plus I will write this H as HX plus AlX4 minus. Okay, that's the mechanism of this reaction. So this species can be said as sigma complex. So this mechanism was supported by the detection of these sigma complexes at low temperature. Okay, let's look on to the one of the aspects of this reaction. Suppose we use this reagent CH3Cl. If we use a Friedel-Crafts acylation reaction, we know that with using a aromatic compound, we will get a monosubstituted alkene. Okay, a monosubstituted aromatic compound CH3. What if the alkyl halide contain more than one equally reactive C hydrogen halogen centers? Okay, so for that example, dichloromethane is an example, that is dichloromethane. So it will react with 2 benzene to form a diphenyl methane. Okay, again, if chloroform is used, again I'll write it here itself. If the chloroform was used, we will get one more substituted here. It will be H itself. I will write this as H and triphenyl substituted triphenyl methane we will get. Okay, what if we are using trichloromethane CCl4? Okay, due to this steric hindrance over here of these species, steric hindrance, here there will not be a substitution of phenyl group. Instead it will be only forming a triphenyl chloromethane only, also known as trityl chloride. Okay, in organic synthesis, this suffers some problems in the applicability. So what are those? First is related to the activating effect of an alkyl group. Activating effect of the alkyl group, substituted alkyl group. Okay, that is the monoalkylated, that product, this product is more reactive than the starting material. Okay, this monoalkylated product will be more reactive than the starting material. So what happened? So it will be resulted in the favors the formation of a di or polysubstituted compounds. And also the scope of the reaction is limited by the reactivity of certain starting materials. Like naphthalene and related polycyclic aromatics is undergo many side reactions, so that may affect the reactivity of the expected reaction. Another problem is also we cannot use the aromatic heterocycles. The aromatic heterocycles are not suitable. Aromatic heterocyclic compounds are not suitable. So OH containing or NH2 containing or OR containing, this will coordinate to the Lewis acid, and so this should not be present in the aromatic ring, and heterocycles should not be present in the should not be suitable for the reaction. Another problem is the rearranged product, either from the rearranging of the carbenium ion or migration of the alkyl substituted aromatic ring. Due to this complication, the more effective way to prepare an alkylated aromatic derivative by conducting the Friedel acylation and then reduce keto group to the methylene group in order to get the alkylated side chain. Okay, the Friedel acylation will be explained in the next video. Thank you.